in order to get onto our lesson, I think I need to give you the big picture. And the big picture is this. We've got this second order circuit. And a second order circuit just means it's got two energy storage elements. Two capacitors, two inductors, a capacitor and an inductor. If we have a step input, also called switched DC, and if we have precisely an R, an L, and a C in series or in parallel, so no two capacitors allowed, you can't have it connected in some sort of way that's not in series or parallel. In that particular case, we're going to use the plug and chug approach. And that is going to be our test tube block. And I'm going to cover this whole thing in a total of 4 lessons. Lessons 15 and 16, that's what we are here, is without a source. In other words, you're going to start off with a RLC circuit in series or parallel that's initially charged up, and then for time greater than 0, it's going to discharge. And how does it discharge? And then for lessons 17 and 18, we're going to add the source. And because there's really not much to adding sources, I'm going to really tell you right here how to add the source. So we really have 4 lessons of practice in solving this whole thing. But that's still a pretty specific subset. Turns out that DC inputs, switched inputs, are so common that it's worthwhile doing this approach. But one of the most common types of inputs isn't switched DC. One of the most common types is with sinusoids. That happens all the time. And for that, we're going to use a totally different method called phasors, which is going to be equal to our test 3 block. The plug and chug, this test block, there's a lot of knowing of keeping track of a particular complex methodology. You'll really use your 3x5 cards for your next test to help you here. For phasors, it's a completely different methodology that really just converts these problems back into circuits 1 problems. So if you felt comfortable with circuits 1, awesome, you'll love it. If you had trouble with circuits 1, hang tight with our reviews of circuits 1 in lab to get there. And by the time you finish this class, you will feel really good with circuits 1. And then the last step is the anything input. And for the anything input, that's going to be a whole new system called Laplace methods, and that is EE223. It's an entire class, which lets you generalize it to everything. And I'm going to do a quick review. Review 1 of calc, specifically disk. Think disk. The derivative of sine is positive cosine. So in other words, if you're taking the derivative of something like sine of 2t, because the derivative of sine is a positive cosine, this is the positive answer. So it's a 2 cosine of 2t. And similarly, the derivative of cosine of 2t, that's the negative one, negative sine of 2t. The other thing I want to review in calc is the product rule. The product rule says that if you're going to take the derivative of 2 functions multiplied by each other, it's the derivative of the first. It's all combinations of taking the derivative of 1. Whoops. It's all combinations of taking 1 without the derivative times the other with the derivative. And the last thing I want you to recall are the constitutive equations for capacitors and inductors. Those are the relationships between voltage and current. And those have those derivatives in them also. So I sub C is equal to C dV dt. Armed with that, I think that the best way to teach this, give me a second, is by looking at the notes that I've created for this class. So you definitely need to take a look at these notes. This is our entire exam test block 2 in the methodology over here. Let me just check that. Let me make this a little smaller. There we go. So here's the methodology on page 1, and then I give you an example on page 2. If you really understand this one page, you've got this whole test block. It's it. Just like if you really understood that one page guide on how to do first order problems, you'd get problems 3 and 4 on the test. So this is going to be the equivalent of problems 3 and 4. This is probably going to be the equivalent of problems 2, 3, and 4 on the test. So let's go over it fast. First is you want to find the initial conditions. Actually, I'm going to just develop it on the fly. I'm going to develop it on the fly with the problem. And I'll make this problem relatively, I think, difficult. We've got a 10-volt constant source attached to a switch. And that switch opens at time equals 0. We've got a capacitor. And we've got a inductor. And we're interested in this current, Isabel. How do we find Isabel? So there's certain steps. The first step is to, let me see if I can pull you back to my overall note card. Okay, so the first step is to find the initial conditions. And unlike first order circuits when there was just one initial condition, that was V sub C or Isabel, this is different. This is 2 subparts. The first is you're going to draw it for time less than 0, and you're going to find both V sub C and Isabel. Now, when you draw it for time less than 0, capacitors are opens, inductors are shorts, no switches or those are supposed to be U of T's. Those all collapse down. And you're going to find V sub C and Isabel. By the way, I've seen, one of the problems I see with cadets is that they draw it at the right regions, but they lose track of what they're trying to find. And if you don't know what you're trying to find, you're not going to be able to solve the problem. So regardless of what you're asked, find V sub C and Isabel. There's 2 things to find. Here's the new part. Draw it for T equals 0 plus. At that moment in time, the capacitor looks, you know what the voltage is on that capacitor. You just found it. So it looks like a voltage source. And you know what the current is on through the inductor. You just found it in the previous step. So now, instead of always finding V sub C or Isabel, you're going to find whatever you're asked to find. I'm going to call this X. Maybe it's a voltage across a resistor or a current through a resistor. But whatever you're asked to, but whatever it is, you're going to find both that value and its derivative. And so that's the new thing. And then the second step is to find the natural solution. In order to do that, you'll draw it for time greater than 0. You'll find the magical numbers omega sub naught and alpha. Omega sub naught is by this equation. Alpha, there's different equations depending upon if the RLC is in series or in parallel. And then you'll construct this weird thing called S, which is minus alpha plus or minus alpha squared minus omega naught squared, using your alpha and your omega naught that you just found. Okay, you're going to compare your values of alpha and omega. If alpha is bigger, it is overdamped. If alpha is equal to omega naught, it's critically damped. And if alpha is less than omega naught, it's underdamped. Then, depending upon which of those situations it is, you'll rewrite your natural part of your answer as one of these 3 equations. You'll notice that for each of these three equations, there is an unknown, two unknowns, C1 and C2. They're just, each equation is different depending upon its damping coefficient. The third step is you're going to find the force solution, which is when you draw it at time equals infinity. At time equals infinity, you're back to DC steady state. And then the last step is to find the total response. You add your natural solution with your unknowns that you found in step 2 to your forced solution, which was just like what you found for first order at infinity. You add them together, you'll have two unknowns. You'll have these C1 and C2s. You'll solve for those using your initial conditions that you found all the way up here at step 1. So you'll have one equation, but with two unknowns, and you'll have two things that'll help you find. You'll know what your value should be at 0, and then you'll know what your value should be, the derivative of your value should be at 0, and that'll find the total response. So let me do it with this complicated example. Different than this example. We'll give you tons of examples in this. This is why it's so important to work all those homework problems, even if it's not collected. What was the question, Sabine?
I was just wondering where in Canvas we can print this out.
Should be in Canvas.
It is in Canvas in the modules.